I've done for the review, okay, is later this afternoon, I'm going to put this same review on Joule that we had for the first test. Okay, this just goes through each of those different chapters. Okay, remember it's going to be on work and energy, heat, waves, and electricity. Okay, goes through each of those chapters, discusses the individual subtopics for each of them. Okay, and then has the corresponding homework problems. Okay, now these homework problems are just those same homework problems I assigned throughout the previous lectures. Okay, but at the same time, if you know, looking at this list right now, that hey, I have a problem with temperature, go back and do these couple more. Okay, because these will go along with that. And remember, this will all be on Joule, so you can print this out. Have it. Not yet. All right, give me a couple hours. All right, this afternoon it'll be up there. Okay, but what is already on Joule, okay, are all the class notes that we've talked about. Okay, besides electricity, which I'll post later today. Okay, so there's work and energy class notes, heat, all right, and waves. Okay. In addition, what I've started doing, why I'm wearing this weird thing right now, okay, is that I've started recording all of our lectures too. Now we don't have a ton of our lectures here, okay, but if you click on this link here, basically this has our most recent lecture about circuits and magnets. It also has everything we'll do today, along with probably a more detailed review. Okay, and so really all this is, I know you guys just love the chance to listen to my lectures.
So far we've learned,
okay,
all right.
What's this is basically just capturing everything I'm writing up here,
today, all right,
along with my voice. This sound weird to yourself, all right? So you can just see everything we did. Now I don't expect you to, watch each of these, all right, all the time. But at the same time, if you do want a little review, if you didn't miss anything I'm saying today, all right, you can go back and watch this. Okay. So that's all that's on Joule. Now let's go over these review topics. Okay, obviously we only have 25 minutes now, so I'm not going to be able to work out all these, all right? But we can go through them kind of quickly. Okay. Let's start with work and energy. Okay. What do we define work to be? Oh, okay. Remember, we said work was force times distance. Okay. This was kind of our next step. Okay. I can apply a force to something like this wall, and even though it's not moving, I'm applying a force. All right. But work says I have to have both a force and a distance. So if I have some guy, all right, who's pushing a box with a force of 10 newtons, if that box isn't going anywhere, how much work is he doing? None at all. Okay? But if that box moves 5 meters, okay, then I can use my equation here and say, well, work is just equal to that 10 newtons times 5 meters, 50 newton meters. And what's a newton meter? A joule, all right? So 50 joules worth of work. Okay? And remember, joules was our unit for everything we did in this chapter. Okay? Because we also talked about kinetic energy and potential energy. What's another one word to describe kinetic energy? Energy in motion, okay? Yeah, that's what kinetic means, basically movement. What about potential energy? Stored energy, okay? And once again, we had equations for both of these, all right? Remember, kinetic energy, EK, was just 1/2 mv squared. So the more mass you have, the faster you're moving, the more kinetic energy you have. Potential energy, we said, can be caused by a lot of things. But when we think about potential energy due to gravity, so we get my favorite equation here, EP is equal to mad. Okay? So the more mass the object has, the higher above ground, the more potential energy it has. Okay. Now the other important thing we said, we talked about the conservation of energy. What does it mean when I say energy is conserved? It's not created or destroyed. Okay? What this means for us is that if I start, let's say, a 5 kilogram bowling ball sitting on top of a 3 meter desk, how much potential energy does that bowling ball have? How would I figure that out? What? Times 9.8. Yeah, because that MAD, remember, is just my mass times acceleration due to gravity, which is 9.8 meters a second squared, times my distance above ground of 3 meters. So when I multiply all that together, I get about 150 kilogram meters squared over second squared, which is the same thing as 150 joules. Okay? How much kinetic energy does that bowling ball have that's just sitting there? Zero. Okay? If something's not moving, it does not have any kinetic energy. Okay? Now let's say this bowling ball falls. It falls here, and now it's 1 meter above ground. If I do this all again, I'm going to get that my potential energy is equal to 50 joules. Where did those other 100 joules of energy go? Kinetic. Good. Okay, so it's all kinetic. Okay. So remember, at each spot along here, there's going to be 150 joules of total energy. At the very bottom, I'm going to lose all this potential energy, and it's all going to be kinetic. Okay. At the very top, it's all potential and no kinetic. But conservation means that that total energy is not going to change. Good. All right. Let's keep going then. Quicker than I thought. Okay. The last thing we did in this chapter was we talked about power. Okay. And remember, power, we said, was just one more step to deal with work. Okay. Power is just equal to work over time. Okay. So it's not just how much work we did, but how fast we did it. So if I go back to that example, that guy applying 10 newtons of force, moving that box 5 meters. So we know his work was just 10 newtons times 5 meters. But if I took this one more step and said it took this person 20 seconds to do this, his power would just be that 50 newton meters divided by 20 seconds, or 50 over 20 newton meter over second, or 2.5 joules a second. What's a joule a second? Watt. Okay? So 2.5 watts. And remember, this watts is the same thing that we saw before. Okay? Same thing for electricity, same thing when we're talking about pushing boxes around.
So power is going to be watts and work is going to be joules.
Yes, power's always watts, work is joules, kinetic energy is joules, potential energy is joules. Okay? Basically, energy is joules. Okay. I know we're moving kind of fast, but stop me if you want to see anything in more detail. Okay? Let's move on to heat. Okay? First thing we talked about with heat was we talked about temperature. Temperature, we said, was the average kinetic energy. Okay? So, like I asked on that quiz, what's moving in that wall over there? And you better know this for the test too. The atoms and molecules. Okay? So we didn't do too good on the quiz on that. Okay? But even if that wall isn't moving on its own, okay, the atoms and molecules in that wall are moving. And that's what we talk about when we talk about temperature. Okay? Now, we did have a couple equations with temperature. We said, okay, the temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus 32. And then we said the temperature in Kelvin is equal to temperature in Celsius plus 273. Okay? But really, these are just plugging in what we know. Okay? Because any of these temperature scales, whether it's Fahrenheit, Celsius, or Kelvin, are all just ways to measure temperature. Okay? They're all saying the same thing. So when I say something is 32 degrees Fahrenheit, 0 degrees Celsius, or 273 Kelvin. All those are saying the same thing, just in different ways. Just like saying that table is 2 meters long is the same thing as saying it's 200 centimeters long, which is the same thing as saying it's almost 2 yards long. Okay? Just different scales. Now, we also talked about heat, and we said heat, all right, was a form of energy. Okay? Why did I talk about donuts when I was talking about heat? Because it has some amount of energy in it. Most of the time, we use that energy to eat, to walk around, to live, whatever. Okay? But at the same time, like we saw in the lab with those Cheetos and marshmallows, if I lit this donut on fire, it would release that energy in heat. Okay? And remember, the only tricky thing about this is that if this donut says it has 100 calories on its label, they're actually food calories. Okay? So 100 food calories is actually 100,000 calories. Okay? And once again, all right, 1 calorie is equal to 4.2 joules. So if I set up this unit conversion, if I want to know how many joules are in this, put what I want to get rid of on the bottom, so calories, what I want to keep on the top, joules, and then all that's equal to 420,000 joules. Okay? So remember, that seems a lot more imposing now. Okay? Good. Now remember, we also talked about specific heat. Remember, that was another equation. We said H equals mc delta T. But that's all well and good, but can you tell me what specific heat is in a word? What does it mean when two things have a different specific heat? Not in a word, a sentence. Kinda. Remember, specific heat, we said different materials absorb heat differently. Okay? This metal feels colder than the wood up top because it absorbs heat differently. Okay? So we said water was our example here. Water has a specific heat of 1 kilocalorie per kilogram degrees C. This means that it takes 1 kilocalorie of heat, 1 kilocalorie of energy to change the temperature of 1 kilogram of water by 1 degree Celsius. Okay? But other things are different. All right? That metal is a lot lower. That means it takes less heat to change the temperature of metal than it does water. Okay? Both things can have heat added to them, but they're going to change temperature differently. This is the same reason we said if you go to the beach on a hot spring day, that sand's going to burn your feet, but the water might be cool. Both are being exposed to the exact same heat, but that sand absorbs the heat a lot quicker than the water. The sand absorbs the heat, changes its temperature a lot quicker than the water does. Okay? And that's what we mean by specific heat. And don't worry, all these specific heat values for water, sand, everything will be on the test. So you don't need to memorize this. We only need to know that specific heat is C.
You don't need to know that specific heat is C?
You just need to know that specific heat is C. Okay? You don't need to memorize what all the different values
Like
are.
mass times specific heat changes
Yeah.
what?
Temperature, yeah. Okay. Okay. Oh, and then the last thing we talked about when we talked about heat, we talked about how do we transfer heat. Okay. Remember, there were 3 different methods. What were those 3 different methods we transfer heat? There we go. Conduction, convection, and radiation. Okay? So this is how we get heat from one thing to another. And really what you need to be able to do here is be able to give me an example of this. Or if I give you an example, you need to be able to tell me which one of these it is. So if I think about the air conditioning in your home, which one is that? Convection. Okay? Because remember, in convection, we're going to heat, or in this case, cool down a small pocket, and then we're going to blow that cold or hot air around. Okay? And that's how we're transferring heat. What's a good example of conduction? A stove. Okay? Stove's probably the best example. A stovetop, all right, you put a pan in direct contact with that hot stovetop, that heat flows through direct contact. Okay? And finally, what's an example of radiation? Sun. What's another one? Microwave. Okay? Remember, radiation is just heat transfer through light. Okay? Good. And so that's all for that heat chapter. That's good because we're running out of time. Okay? Finally, let's get to the waves. Okay? Waves, I was really surprised that everyone did not do as well as I thought on this last test or this last quiz. Okay? Because really, there's a lot of memorization in waves, and maybe that's what you weren't expecting so much. Okay? There's a lot of concepts here. But remember, one thing all waves have in common, okay, is they all have a few basic properties. So this is something we need to know. Okay? The wavelength is how long a wave is. Okay? The period, measured with a capital T, is how long it takes for that wave to pass by. And then finally, the intensity, or how big a wave is this amplitude. Okay? So you need to be able to tell me things like, okay, if I start shouting at you, which one of these changes? No. The amplitude would change. The amplitude describes the intensity of the sound wave. Okay? But at the same time, what if, I don't know, instead of being white light, these lights suddenly change to blue? What would change there? Frequency would change. What else? Yeah, the frequency and period would change as well as the wavelength. Okay? Good. And remember, we didn't put frequency on here, but frequency is just 1 over the period. Okay? So remember, frequency says how many waves pass in a second, and period says how long it takes for one wave to pass by. So they're both saying the same thing, just in slightly different ways. Okay? Good. Remember, the other thing we also said is all waves are traveling. So the velocity of a wave is equal to its wavelength times frequency. Now, some waves travel faster than others, right? Okay. What travels faster, light or sound? Light. How do we know that? What's a good example? Lightning. Okay. We see lightning before we hear it. And I'll put this on the test. I'll say the velocity of light, it's probably exactly how I'll put it on the test, v light equals 3 times 10 to the 8th meters a second. So anything that's light, okay, travels at 3 times 10 to the 8th meters a second. While anything that's sound travels at around 344 meters a second in air. Okay. But this means if I give you a question like this, you'll have to know if it's light or sound. If I'm talking about radio waves, are radio waves light waves or sound waves? Light. Okay. Remember, radio waves are light waves that carry sound information, but radio waves travel at this 3 times 10 to the 8th meters a second. Okay. If I, on a tangent here, if I pull up to your car at a stoplight, okay, and I have my music blaring as loud as it can, and you roll up your windows, what are you more likely to hear? What type of sound? Bass. Why? It's got a lower frequency. Lower frequency, which means it has a longer wavelength. Remember, those longer wavelengths can more easily pass through things. Okay, remember that example we did in class of me with that wave and someone throwing something at me? Okay. Yeah. Well, in reality, if we have a nice long wave, all right, it's easy for that wave to pass through something without getting hit. Okay. It's easy for something to go right past that wave without anything happening. But if we're moving that wave up and down really quickly, then that wave is more likely to hit something. Okay. And that finally brings us to our most recent chapter about electricity. Okay. Remember, once again, we have a bunch of definitions here. Okay. Because remember, we said electric charge. What do we know about electric charge? Nothing. We know nothing about electric charge. All right, that's good to know. If I have a positive charge and a positive charge and I put them close together, what's going to happen? They're going to repel, right? Because just like we were just talking about magnets, okay, like charges repel. Okay? And that must mean that opposite charges attract. And remember also, when we're talking about these like charges and unlike charges, all these charges really only come from two places. Either electrons with their negative charge or protons with their positive charge. Okay? So when I say something has an electric charge or is negatively charged, it means it has an excess of these electrons. So the positively charged has an excess of protons. Because in us right now, there's all sorts of electrons and protons. But for the most part, they're balanced. Okay? It's only when they get unbalanced that we notice this. Okay? And we also started talking about things like current. How would you describe current to me? Charge in motion, okay? The flow of charge, the flow of electrons, okay? It's charge over time, all right? Because our equation we had for that, and you're absolutely right, all right? Current is equal to charge over time. Okay? It's how much charge moves in a given amount of time. Okay? Why do charges move? What do we need to have in order to have current? How do we get electricity, though? Not just current, we also need voltage. We need voltage. Okay, voltage is the reason we have charge moving. All right, we have to do something to separate those charges to begin with to make them want to come back together. Okay, and that's where voltage comes into play. All right, and then remember we ended last week with Ohm's law, okay, and the power law. Okay. So just remember, if we know any two of these, we can get the other two. Voltage equals current times resistance. Okay, power equals current times voltage. And remember, the only thing to be careful of, which I might be a little tricky, all right, is that this is voltage measured in volts, current measured in amps, resistance measured in ohms. So if I give you something like, I don't know, 3 kilovolts, okay, and 2 mega ohms, probably won't give you mega because we don't need to memorize mega, but you'll have to convert them first.
So say that one more time, voltage is measured in?
Voltage is measured in volts, current's measured in amps, resistance is measured in ohms. Okay, and so power is measured in watts, then current in amps, and voltage in volts. Okay. Good, good.